Next problem I want to do, I'd like to look at number 22. So here's number 22. It says, here's a region of integration of the integral, and they give us the figure associated with this problem, and here it is. And from what we see, it seems they really went with dz, meaning they ran from it's really hitting at 0, and it's exiting out of z equal x squared. So when I do that, I'm really looking now from the bottom up, and this is what I see. I see x running from 0 to 1, but y running from 0 to -1. I only see this rectangle. They did y run from negative, oh, that can be right. They ran y from y equals 0 to y equals 1. That's not matching. Okay, I think that's a typo. I'm almost certain. There's no way that could work. Y runs from -1 to 0, and x runs from 0 to 1. I think they meant this to be dy and this to be dx. I think they got them backwards. But anyways, let's continue the problem. Let's see. We'll figure that out once we get the rest. This is what they want. They want us to continue and fill in all of those. Rewrite the integral as an equivalent different order. That's really annoying. That's odd. Okay, let's go by the first one. Actually, let's get e out of the way. And the reason I want e is already right there. All what I have to do is really rearrange those, since z is already set. Z is already from 0 to y squared. Now I want dy, then dx. Well, if I want dy as the outsidemost integral, that would run from -1 to 0, and x would run from 0 to 1. So that's one. Secondly, if I go by this, if we want to run in the y direction, then I'm really looking at y is the insidemost function. If I run from the y point of view, y is going to hit at y equal -1, and it's going to exit out of, what would that equation be? If z equal y, y would equal plus or minus radical z. In this case, y is negative radical z, because y is to the left of the origin, right? This is y being positive, this is y being negative. And if that's the case, then I'm really looking at nothing more. The only thing I see is a rectangle in the x-z plane, in which x runs from 0 to 1, and z runs from 0 to 1. So here, it doesn't really matter how you run this. You could say dz runs z from 0 to 1, and x from 0 to 1. Remember, a rectangle I could really swap easily once I fix the 3D and get a 2D, I could really switch those, and they're going to be the same because this is not any rectangle, it's a square. Alright, I made that mistake again. And so I'm guessing that would be B. That's B right there. And that's A. And if I go for the third portion, if they want to run in terms of X, well, let's see how this works. If I run in the X direction, and let me go back to the graph, in the X, I notice I enter out of X equal 0, and I exit out of X equal 1. And if that's the case, I'm really looking from that side at what? X, there's the positive X axis, there's the there's the Y axis, and there's the Z axis, and this is wrapped and bound the negative Y, so it looks like this. And that is either Z equal Y or Y equal negative radical Z. And this is negative 1, and this is 1. And we're talking about literally this region, corresponding to this region, right? And this part right here really corresponds to this part right here. And this part right here corresponds to this part right here. So, this would be two ways I could do that. Well, might as well just get them out of the way. So we said, in the Z direction, I could go from 0 to 1, and let's see. Either I say, let Y equal negative 1 to Y equal 0, and Z run from 0 to Z equal Y squared, or run this from Z equals 0 to Z equal 1, and Y would run from negative 1 and exit out of negative radical Z. And there it is. The 6 different ways I could write this. Let me just move this later. And you could do that pretty much on every problem. Now, if they say do that, then you should. On the test, I'm going to ask for 3 of those. I'm going to ask one in the X direction, one in the Y direction, one in the Z direction. So C would be, where is it? This would be C, the way I did them. And that last piece would be D. And that's all the different combinations I could really write this in. I could write it in 6 different ways. And you should familiarize yourself with all 6 different ways. Again, I'm going to have you do 6. I'll just have you do 3, but then I'm going to do the X, the Y, and the Z. Next problem I want to look at is number 26. Directions. Find the volume. Now there's a list of problems that you could practice if you really want. But I suggest you just follow what they want, what they ask. You will have a homework problem that will ask, oh boy, it happened again. Okay, sorry, I'm still learning how to use this. It seems if you click a button, somehow it freezes. And I got what it is now, finally, after all this time. So, if I look at problem number 26, they give us these planes, and the beauty of those, they give us the actual figure associated with this. And here it is. Now, you could do this any way you want. We are used to running this vertically. That is, you could write this any way you like. I'm going to say, find the volume. Volume is going to equal a triple integral. And why not tackle this the way we've been working all along? Get z out of the way. So based on what they gave us, this right here, oh, this is cut off. I'm sorry. That's an actual, let me fix that. Oh, okay. Take this out. Oh, come on. Okay, there. So run this in the z. Okay, just kidding. Run this in the z direction. That means z would run from what? Z equals 0. And where would it exit out of? Do you see this plane right here? That's a plane. So you have a cylinder coming out, a cylinder running vertically, right? And a laser coming at z equal negative y and just cutting that, creating what you see. Once you do that part, once you get that part out of the way, now you're looking at this in 2 dimensions, and we are comfortable with x and y because we've been dealing with that all along. Now, how does this look like? There's x and there's y. Do you see that this is around the negative y-axis? This is y being positive, negative. Okay, that doesn't look like a circle. There we go. And we're talking about this ground, the ground on the floor. Okay, and how does that work? Well, this is y equal negative the square root of 1 minus x squared. So why not do this the most traditional way? Run x equal from negative 1 to 1 and have y run from negative the square root of 1 minus x squared and exit out of 0. And there it is. Any one way will do, and I'm going to assume you could work this out. I'm going to try and set those up. Alright. And if I wanted to tackle another problem, let me look at problem, oops, wrong page. Let me look at problem number 28. I want to do 28 and 32. Again, I could do this so many different ways. Oh boy, here it goes. Okay, it's doing that again. In the Stewart book, this problem was there, and they said to do it 6 different ways, and one of the ways was a disaster. That's in the direction of x. Well, why not, again, if I have an option, why not just do it the way I'm used to seeing this? Oh, come on. Why not say volume equal the triple integral and run z? Why not run from 0 and exit out of the cosine of pi x over 2? If I did that, then I'm really looking at the 2 dimensions, right? And from the floor up, what do I see? I see x at 1 and this by 1, and we're talking about this floor region right there, which is this. Right? They're both positive, correct. And that is y equal 1 minus x. Well, can't I say that x run from 0 to 1? And y would run from 0 to 1 minus x. I wanted to do one more, but I am out of time. I really wanted to do number 32. But it's all good. I'll assign it in the homework. You guys could do it. Alright, I'm going to add the homework. And there's your homework. Hopefully it will let me upload it, otherwise I'll have to cut this out, but I'll add the PDF.